As we've mentioned earlier, we said that in general, the higher the temperature, that when you do your reaction, the higher the rate constant, you get a higher rate constant and a faster rate. Why is that? Reactions occur because of collisions, right? So the higher the temperature, the faster the molecules or atoms are moving, the more often they collide. They have more energy to overcome what's called the energy of activation, the minimum energy you need for the reaction to occur. Okay? Arrhenius used what's called an empirical equation. That's just based on experimental observation. He was able to fit experimental data to this equation. K, the rate constant, is equal to some constant A times e to the negative e sub A. E sub A is called your energy of activation divided by RT. Okay, so that's how he was able, that's the equation he used to relate, to summarize experimental data that shows how the rate constant depends on temperature. Let's look at this equation. If you were to take the natural log of both sides, natural log of K equals natural log of A, okay, plus the natural log of this expression right here. What is the natural log of e to the negative EA over RT? In other words, what's the natural log of e to the x? It's just x, right? So the natural log of e to the negative EA over RT will just be this thing that's inside the e. So that's minus EA over R times 1 over T. So this is another way you can write your Arrhenius equation. So the Arrhenius equation relates the rate constant with temperature. So ln of K is equal to ln of some constant A minus energy of activation over R times 1 over T. Okay? Now, if you were to plot your experimental data, so you do a series of runs, everything identical for those experimental runs except for the temperature. Okay? So, and you're able to get the rate constant at each temperature. Okay, so you have a series of experiments. If I were to put this in my y-axis, natural log of K, and I put 1 over T on my x-axis, y equals mx plus b would be the equation for a straight line. What is negative EA over R? That's your slope. And ln of A is going to be your y-intercept. So if you were to make this plot, let me give this a little more room here. If I were to plot natural log of K versus 1 over T, I'm going to get a straight line with a slope equal to negative E sub A over R. In other words, if I want to determine my energy of activation, all I have to do is multiply my slope by R. What's the value of R? 8.314 joules per Kelvin per mole. Okay? So and what would be the y-intercept for this one? It's going to be natural log of that constant A, the pre-exponential factor. That depends on what the reaction is. Okay? So how do I get the slope of my line? I just need 2 points, right? I need to identify 2 points on the line to get my slope. First of all, let's see if this is consistent with our notion of rates being faster at higher temperature. 1 over T, okay, at very high temperature, what's my value of 1 over T? The bigger that denominator is, so this one right here, this side of my graph represents high temperature, okay? The smaller that denominator is, 1 divided by a smaller number would give you a bigger overall number. So the right side of this graph represents low temperature. So is that consistent then with what we expect? At high temperature, you have faster rates, okay, larger rate constants. At low temperature, you have lower rate constants, okay, slower reactions. So how do you determine the slope? Delta y over delta x, right? So So delta y over delta x. What's delta y? ln of k2 minus ln of k1. Pick 2 points, 1 and 2, right? Divided by 1 over t2 minus 1 over t1. Okay? And what's that equal to? That's equal to negative e sub a over r. Okay? So that's one way you can determine your slope. From your experiment, you can calculate this. But what is ln of k2 minus ln of k1? That's what's another way we can write this. This is ln of k2 over k1. Remember? ln of x minus ln of y is ln of x over y. So divide that by 1 over t1, 1 over t2 minus 1 over t1. That will give you negative e sub a over r. So whatever this is my slope. You just multiply that by negative r. That will give you your energy of activation. Okay? Let's rearrange this equation in something you might see in your textbook. You'll see this written as ln of k2 over k1 equals negative e sub a over r. I'm going to move this thing right here over to the right side, so that's going to be 1 over t2 minus 1 over t1. So this is another form of the Arrhenius equation. Okay? So if you know k at t2 and k at t1, you can solve for the energy of activation. It's just negative r times the slope. Okay, so that's how you determine your energy of activation. Here it is. Slope is ln of k2 minus ln of k1 divided by 1 over t2 minus 1 over t1. All right? And ln of k2 minus ln of k1 is just ln of k2 minus k1. What's the unit for your slope? Let's look at our slope. What's the unit for the numerator here? ln of k2 over k1. The unit of k2 and k1 will cancel out, right? So your numerator is unitless. What's the unit for the denominator? 1 over, what's the temperature unit? Kelvin. Make sure you plug in numbers in Kelvin. So this is 1 over Kelvin. So the unit for your slope is Kelvin. Okay? This is the temperature unit. So, like I said, E sub A, energy of activation, is just going to be negative R times your slope. And this is in Kelvin. Okay? And your R is joules per Kelvin per mole. So if you multiply the two, your energy of activation would be in joules per mole. That would be the unit for your energy of activation. Let's take a look at this example right here. ln of k versus 1 over t. Look, okay? Estimate the rate constant at 25 degrees and 95 degrees. What would you have to do? What's 25 degrees? 298 Kelvin, right? So 1 divided by 1 divided by 298 Kelvin. 298 Kelvin is 0.003356. That's 1 over 298. Where is that on my graph? It's 0.03033. So it's down here, somewhere down here. Okay? And so that would be my ln of k there. And then k will just be e to the ln of k. At 95 degrees, where would I be? What's 95? 1 over 368 would be 1. 1 divided by 368. 0.00271. 1 over 368. 0.00271 is right here. That's at 95 degrees. So this is the data at 95 degrees. Down here is the data at 25 degrees. Okay? So here's a graph of ln of k versus 1 over t. You have the slope and the intercept. What would be the energy of activation for this? Minus r times the slope, right? So what's our r? 8.314 joules per Kelvin per mole. And what's our slope? Negative 6014. That should be in Kelvin. So that gives us 8.314 times 6014, 50,000. So 50,000 joules per mole. That's about 50 kilojoules per mole. That's typical for most reactions, around that. And with that energy of activation, the rule of thumb is to double the rate of a reaction, you have to raise your temperature by 10 degrees. So at 25 degrees versus 35 degrees, you usually see a doubling of the rate of reaction. And that corresponds to an energy of activation somewhere around 50 kilojoules per mole.